what are we going to see today? Three topics. Actually, the first is proportions, a special type of proportions questions that I will illustrate at the beginning, then rates, and then some questions using or involving algebraic expressions. All right? So let's begin. What are we going to see talking about proportions? The questions about proportions mean something like this, okay? Imagine that you have a triangle, okay, and the area of that triangle is this, described here. Area is 1/2 of base multiplied by height, right? It's a very well-known formula for the area of a triangle. Now, let's say we triple the height. That is to say, the initial height gets multiplied by 3. What happens to the area? By which factor is the area gonna be multiplied? That's a question, actually. We need to find a factor that represents the increase of the area in terms of the old area or the initial area. Something like, for example, saying the new area will be this factor x multiplied by the old area. How would we find this? Do you want to try? Okay, give 1 minute. Okay, let's see. What are we supposed to do here? Take a look at this. If we triple the height of the triangle, the new height would be 3 times the original height that was h. So the new area would be 1/2 of the base times the new height. But if we, take out the factor 3, we can see that the expression is the same as saying 3 multiplied by this expression, which we know to be the original area of the triangle. That is to say, the old area. So actually, the new area would be triple the original area, or 3 times the original area. That is the type of proportions questions that we intend to see today, okay? So let's see some other cases. Okay, some of them will be more elaborate than this sample question. Take a look at this. The radius of a circle is increased by 25%. By what percent does the area of the circle increase? Okay, can you try to solve this one? How would you do it? Let's here pause for a moment so that you can try, okay? So here we are asked for the percent that the area of the circle would increase, right? Similar to what we said, okay, the area of the triangle would be tripled, right? If the height is tripled, that would mean an increase of 300 or 200%, right? That would be the increase of 200%. What percent would the area increase if the radius is increased by 25? Well, this assumes that you all know, like the formula for the radius of a circle, right? Well, I think that everybody knows that. Let's see how to do this. So if you, the idea is to get a number right in front of the old formula, something like this, that you say, okay, the new area of the circle equals like 1 plus x% multiplied by the old area of the circle. How can we get that? Take a look. So if the original area is this, then after increasing the radius by 25%, that means we multiply the original radius by 1.25. So this would be the new radius. Take a look. If you now calculate the area of a circle with this radius, what would be the area? It would be pi multiplied by the square of the radius, because the old or original area is pi times the square of the radius. So now that we have increased the radius, if we square this new radius, what we get is, the square of a product is, we multiply this 1.25 by itself, also the radius by itself. And of course, we can rearrange the terms in this way. Notice that I'm changing the order of factors. Just pi multiplying it next to the square of the radius. So take a look. What is this? This is actually the old area or the original area of the circle. So what we get is the square of this number, which is this, multiplying the old area. So saying that the new area is 1.56 times the old area, what does this represent in percent? Remember that what we want to know is the value of x here. The new area will be 1 plus x over 100 times the old area. If we match this factor with this, obviously the value of x gets to be 56.25. That's the percent, right? That's our percent. The percent increase is 56.25%. So this is the type of question we are analyzing today, proportions questions. Okay, sometimes the formula, for example, the area, right, will involve more than one variable, or as we can see here, one variable that is squared, okay? So we need to consider that. For example, here, when we take the square of the new radius, we have to square both the radius, the old radius r, but also the constant value 1.25. What is your question, Axel? You can open your microphone because I cannot hear you. Yes, that's right. Axel is asking class that whether we can use the calculator. In this type of question, we can. Usually we can, okay? Normally, because to calculate the exact value of percents like this, it would be too long. So normally they clarify that we can use a calculator. Okay. Remember that in this case, we're supposed to input the value of the percent in the box, right? It's like a box with a blank. And in this blank, you exactly need to input this 56.25. Don't input 0.5625, okay? Because that is not the percent. The percent is 56.25. Well then, let's see now another question. We have the length of a rectangle is increased by 20%. The width is decreased by 20%. Which of the following accurately describes the change in the area of the rectangle? So basically, what you have is, a rectangle is something like this, right? This geometric, oh, sorry. This doesn't look like a rectangle. You have the length and the width. They are telling you that this rectangle will change. The length will increase, but the width will decrease. So here you can see this will be the old length increased by 20%, but the width of the new rectangle will be decreased by 20%. So what happens to the area? If this is the area of the original rectangle, what will happen with the new rectangle? What is this area A prime regarding the original one? Increased, decreased, or the same? What do you think? That's the question. Notice here, right, that we can approach this question in the following way. Take a look. Okay, so if the area of the rectangle is base times height, that is length multiplied by the width, okay, this product, then the new rectangle will have two dimensions that can be expressed like this. For example, the original length L increased by 20% could be now represented by this expression, 1.2 multiplied by the original length. Now, the original width was W. The new width is decreased by 20% regarding the original width. So it is the original width multiplied by 0.8. So the new rectangle will have an area that is the product of these two dimensions, the new length and the new width. So this product here can be rearranged like this. If we separate 1.20 and multiply it by 0.80, then we get this product of two constant values, which is 0.96, multiplied by L times W, which is the area of the original rectangle. So now you can see that the factor here gives us the percent change. What does it mean, 0.96? It is 1 minus 4%. So that means there was a decrease of 4%, right? The answer is option C. Well, let's see another question. Okay, this time I will not say anymore. You can read the question on your own, try. You'll have like 2 minutes. Example 3. Okay, unless you don't see well any words or something, you can try this one. Okay, let's go over this the solution. Okay, let's read. There is a formula. It's 9 multiplied by Q1 and multiplied by Q1 and Q2, and the product of the three factors divided by the square of R. The force of attraction between two particles can be determined by the formula above, in which F is the force between them, R is the distance between them, and Q1 and Q2 are the charges of the two particles. If the distance between two charged particles is doubled, the resulting force of attraction is what fraction of the original force? So they're asking you this, okay? If this distance, the original distance R, is doubled, that is to say, it becomes now 2 times the original distance, what would happen with the original force? The original force would change to a new force that we can call F prime. What is the relationship between F prime and F? So we want to get something like this. F prime is 1 factor X multiplied by the original force F. What is the value of this? Let's find it, okay? It's like this. Take a look. If we substitute the new distance where the old distance appear, that is, instead of R, we place 2 times R, notice what happens. If you develop this, what you have, you can separate this 2R square as 2 squared times R squared. And the 2 squared, you can take it out as a factor, which would actually be 1 over 2 squared, right? But 1 over 2 squared is the same as, obviously, 1/2 squared. So separating this, let me show you the intermediate step, right? It's like saying this is 9 times Q1 times Q2 divided by 2 squared times R squared. If you take this out, it's like this exactly, right? 1 over 2 squared times all of this, 9Q1, Q2 over R squared. So this is the factor that we are placing out, which is actually 1/4. So since this expression matches the value of the original force F, we can say that the new force is 1/4 of the original force. So this is the correct answer choice. Okay, let's now continue with the next example here. Let's see, any questions, any doubts? Please, if you have any questions or something not clear, just raise your hand or you can participate, okay? Madeline, please, what's your question or your comment?
I think like you put the square root like in a half, but you also left the like. Do you also leave it on the other part? Like, I don't know if I'm making myself clear.
You mean here?
Where?
Don't worry, you can ask in Spanish if you feel confused. Okay, no problem.
No, it's just that I really don't know how to say it. Like in your second step, the square la potencia, it's
The
like
power.
in both the power, it's in both like the half and in the like above part of the other.
Here?
No, in the other one.
Here?
Yeah.
Yeah, what about that?
I don't understand why it's like in both of them, like this the power. Like the power it's both in the half and in the denominator.
Okay, you see, do you understand why we place 2r in the position of the new distance, right? Because it says that the original distance has been doubled. Okay, what happens when you square 2 times r? Isn't this what happens?
Yeah.
Which is actually 2 squared times r squared, because the square of a product, right? 2r means the product of 2 and r. So that's 2 squared times r squared. But now what I'm doing here is taking out the 2 squared as a factor that multiplies the whole expression in brackets. Okay? Saying 9q1 times q2 over 2 squared times r squared is the same as saying 1 over 2 squared multiplying the whole thing, because when you multiply two fractions, what happens? Multiply numerators, you get 9q1 q2, and multiply denominators, 2 squared times r squared, which is exactly this. Is that right? Understood now?
Thank you.
Okay,
Yeah.
perfect. Okay, let's now keep going, okay, and see next question. The volume of a cube is tripled. The length of each side must have been increased by approximately what %? Okay, probably this is assuming something that you perhaps know or perhaps you don't. But what is the formula of the volume of a cube? You know, a cube is this figure, is a solid shape that has 3 dimensions, right? We always represent cubes like this. A cube has the characteristic that has a common edge, that is the length of this border, that is called the edge, is common. All edges of the cube is the same. Let's say that the size of this edge is S. So what is the volume of the cube? In terms of the common edge S, it would be the cube of S. That's the volume of a cube, okay? In terms of the length of the common edge. Well, having said that, the question is there. Please proceed. Okay, anyone got the answer? Remember, you can use calculator, okay, just in case. Or Excel if you want. Yeah, actually the calculator you will have in the exam using this special software, the Blue Book. You can use, it's like a kind of a scientific calculator. It allows you to take square roots, cube roots, etc. Okay, it's very complete. So if you can use Excel, no problem. So how do we calculate what they are asking? Let's take a look. So the volume of the cube is the cube of the common edge. What is the answer to this question then? We can understand this in several steps, okay? First, the volume of a cube is the cube of the common edge, or the length of the cube of the length of the common edge. So imagine that we want to increase the size or the volume of a cube. Increasing the volume of a cube would imply increasing also the length of the common edge. Let's say that we increase, right, the length of the common edge of a cube by some factor that we call x, right? So the new volume of this cube would be the cube of the new edge. And if the new edge is the original edge s multiplied by a factor x, notice what happens. Because we have the cube of a product, then we can apply the exponent to each of the factors in this product. It would be the cube of x times the cube of s. So, because the cube of s is actually the original volume of the cube, then we can say that the new volume of the cube is always the cube of the factor by which we escalate the original edge multiplied by the volume of the original, or the original volume of the cube. Since the problem is saying that this volume is tripled, they are saying this. They are saying that this factor over here is actually 3, because the new volume will be 3 times the volume original, or the original volume of the cube. So if x cubed is supposed to be 3, you can find this factor, the increased factor for the edge of the cube, taking the cube root of 3, which is about 1.44. But if the increase factor is 1.44, this means a percent increase of just this part, right? 0.44 or 44%. So the correct answer here would be approximately 44% increase for the common edge of the cube. Answer, or option D. Any questions? Well then, let's move on to the next problem. Okay, now that's the last example for this type of question. And now we'll move to the next topic of today, which is rates. Now, what is a rate? How do we define a rate? A rate is a quotient of two quantities that are expressed in different units, each of them. For example, if I have this relationship of two variables in a problem, for example, the number of gasoline gallons versus the number of motor vehicles in some country or city, for example, the number of gasoline gallons consumed divided by the number of motor vehicles in a city, that is a rate. Or for example, the number of miles that a car can, travel per, hour, miles over hours. That's also a rate. Or when you say, for example, if we talk about purchasing some goods, imagine if we want to express how many pounds of, let's say, apples can we get per dollar, okay? Or for example, we have 50 pounds of apples for which we pay $12. Okay, this quotient is a rate. So rates appear in a number of situations in the SAT. Usually, the questions about rates involve actually rate conversion. That is, from one initial quantity, we want to know how this quantity in some specific units is connected to another quantity in other or another unit. For example, imagine that they ask you to convert 1,760 feet per minute to miles over hours. Considering that there is this equivalency between miles and feet, how can we find what they're asking? The strategy we can use to, pass from one type of unit to a target unit is the use of a multiplication or successive multiplications by different conversion factors, as many conversion factors as we need in order to achieve the necessary conversion. For example, clearly you see that in order to achieve this conversion, we need to convert feet to miles and also minutes to hours. So we are using here two conversion factors or conversion rates. The original amount expressed as a rate, that is 1,760 feet over minute or over 1 minute, we multiply by this conversion rate, which is 1 mile over 5,280 feet, meaning there is an equivalence between the two of them, right? Why do I multiply by the factor in this way? Notice that I placed the two terms of my rate, that is the numerator and denominator, which are in different units. I place them strategically. What do I mean strategically? Notice that by placing the equivalence or the terms that are equivalent in this conversion factor, miles over feet, in this way, I guarantee that in the multiplication by the original quantity, this one here, what will happen with feet? Notice that feet will cancel with feet. So that's why I place this conversion factor here. I place in that order. I didn't place 5,280 feet over 1 mile. It is true that that is also true as an equivalence, but I decided to place it in this way for the feet units to cancel each other. Now, what happens with the conversion of minute to hours? I will use another conversion rate, conversion factor, 60 minutes divided by 1 hour. They are the same, right? But I place strategically minutes in the numerator so that when we do the multiplication, minutes will cancel with minutes. So in the end, the only units we are left with are these, miles above and hours below. So we will get the desired units in our rate, miles divided by hours. And the numerical part is simply the same operations you do when you multiply fractions. It is multiplying, I will write it over here, 1,760 times 1 times 60 divided by 5,280, right? Times 1, of course. You can do this very easily with a calculator. and you can get the result is just 20. Okay, so that's the approach we'll use to solve the next rate questions. We'll see several ones to illustrate how this goes. Example number 1. A bicycle manufacturer can produce 20 bicycles per hour. How many hours would it take the manufacturer to produce 320 bicycles? Notice that we start, okay, from some information, which is one rate, bicycles per hour. This rate will be useful to do the conversion that they require in the question. And what is that conversion? Notice, we want to go from this target number of bicycles, we want to find the corresponding number of hours for achieving that production. So we can say that if we have 320 bicycles, we want to obtain here X hours. How can we find the correspondence between the bicycles and the hours? Simply by using the conversion rates that appears here in the statement prior to the question. If we multiply this by this, we can say, in 1 hour, how many bicycles are produced? In 1 hour, just 20 bicycles. How do I place the conversion rate like this? Well, because I want bicycles to cancel. So I am left with hours only, right? If you do this, you can get this right. Okay, this doesn't need a calculator actually, 32 divided by 2, and you get the value, right? This is 16 hours. Yeah, perhaps you say, this is like weird. What I would have done is divide directly 320 by 20. It's true that sometimes common sense is faster, but if you always use consistently the approach I'm using here, you can solve any rate question, no matter how complex it may appear. I think there is a comment. Okay, Axel was suggesting the correct answer. That's it, 16 hours. Okay, this is an example. So let's try to use the same approach in example number 2. Now you will do it, okay? Example 2. A rocket has 360 gallons of fuel left after 2 hours of flight, and only 100 gallons after 6 hours of flight. It burns n gallons of fuel for every hour of flight, where n is a constant. What is the value of n? Okay, so this is the question. Let's make a pause there so you can try it. Okay, this question requires us to find the value of n, which is a rate, okay, is the number of gallons of fuel consumed per hour of flight. In order to determine the rate of n gallons for this rocket, we can actually calculate this rate using this approach. Any number of or amount of activity completed divided by the time that it takes to complete it. In other words, you can say that in the problem that we are given, this rate n can be obtained by knowing a number of gallons consumed divided by the change or the time of flight for this rocket. We can know this value and this value if we analyze carefully what the question says. If this rocket had been flying 2 hours, okay? And then they say that they check the fuel it had left after 6 hours. So how many times are between this checkpoint and this checkpoint? How many hours? You know, if we subtract 6 minus 2, that is actually 4 hours. In 4 hours of flight, what was the consumption? If after flying 2 hours, the fuel left was 360, okay, how much fuel was consumed in these 4 hours? Okay, it is whatever difference results between this and this value. If after 2 hours, this was the amount of fuel left, and after 6, this was the amount of fuel left, that means that in that difference of 4 hours of flight, the consumed fuel is this, 360 minus 100. In other words, 260, right? And this divided by 4. So, as several of you said, this is half of 130 or 65, the value of it. All right, let's now see another example. Question 3. A box at a supermarket can hold 6 oranges each. Each orange costs 20 cents. Given that the supermarket has a budget of $500 to stock oranges, how many boxes will the supermarket be able to completely fill? So notice, right? We want to map money, $500, to a number of boxes. How much is this money? In boxes. Okay, in boxes of oranges, of course. But we have several conversions that would need to be done, because we know that a box has 6 oranges. We have also the cost per unit of orange. And so we need to do some conversions before we can do this transformation. All right, you can try it. Okay, thank you for your responses. The thing is, how do we formulate the solution of this question? I use a similar approach to that in the first example, okay? I want to convert money, $500, to boxes of oranges. But before doing a direct conversion, I have you know, one or a couple of intermediate conversions. Why? Because, for example, first, the oranges prices is given in cents, not in dollars. So first I need to convert these $500 to cents. How do I achieve that? By multiplying by a conversion factor between cents and dollars. We know that 100 cents is equivalent to the price of $1, right? This goes without saying, of course. Why do I multiply by this factor? Multiplying by this factor will allow me to have the original budget expressed in cents rather than in dollars, because here dollars and dollars will be canceled. So I will get cents. Now, once that I got the money in cents, I can convert this money in cents to the real quantity of oranges that can be purchased. How do I achieve that? I use this information to formulate another conversion factor. I can say that one orange costs 20 cents. Why do I place a factor like this and not upside down? Because I want cents to cancel with cents. Notice, cents and cents. So the product of these three factors will yield the number of oranges that can be purchased with $500. But I'm not interested in the number of oranges. I'm interested in the number of boxes of oranges, right? So there is one last conversion factor missing here. I need to multiply this by another factor that expresses the conversion or equivalence between boxes and oranges. And since they tell me that one box holds 6 oranges, then I will multiply by this factor now. One box over 6 oranges. Why do I place it like this? Because I want oranges to cancel with oranges. And now all I have to do is this product. Now you notice how all the units got canceled and the only units left is boxes. So this will yield a number of n boxes. And how do I get this n? By multiplying 500 times 100 times 1 times 1 divided by 1 times 20 times 6. This is the value of n. So what is this value? Take a look. The value will be 416.67. This is the exact value of boxes. Well, we need to provide in our, response box exactly this value, okay? Why? You may say, but teacher, how can you say 416.67? Well, it's true that it doesn't look like a possible number of boxes, but here the question doesn't say approximately. It just says how many. So this is the exact number of boxes. If it said approximately, you would say, okay, it would be about 417, right? 417, approximately. Okay, that's it. Any questions? Important thing here, rather than the accurate value, is the formulation of the solution, right? The successive multiplication of the original amount here, this budget, by the conversion factor so that at the end I obtain boxes, okay, instead. Well, let's move on. Another practice question. Example 4. A car can travel 1 mile in 1 minute and 15 seconds. At this rate, how many miles can the car travel in 1 hour? So you can see the question, okay? Such as, I want to know, knowing the information that is stated about a car, how does 1 hour translate into a number of miles, knowing what I know about this car? This can be achieved also by using a successive multiplication by conversion rates. Okay, how can we do this? Look, there are 2 ways to do it. One is shorter if you are familiar with the equivalence between hours and seconds, because in the end, we have an equivalence between miles and seconds from this first statement. Okay? We know that if we can convert first hours to seconds, then we can use this rate to determine the number of miles. For example, I know that in 1 hour, there are 3,600 seconds. And they tell me that in 1 minute and 15 seconds, that is to say 75 seconds, the car can do a mile. So another conversion rate would be 1 mile over 75 seconds. Now you see, hour cancel with hours, seconds with seconds, and we get miles. What is the value? Is 3,600 multiplied by 1 and 1 divided by 1 times 75. In other words, this. This is the value of X, the answer to the question. What is that value? Okay, you can use a calculator, no problem. Sometimes it's possible that someone says, oh, I don't remember, I'm confused by this. So what about if I use a two-step conversion for hour to seconds? You can also say this if you want. 1 hour, first convert it to minutes. You say 60 minutes per 1 hour, and then convert minutes to seconds. You can say, okay, 1 minute is 60 seconds. And then, okay, seconds to miles. So 1 mile equals 75 seconds for this car. And this product, of course, will yield exactly the same value in miles, okay? Because by using just this conversion factor, it's like replacing these two, right? These two factors together. It would yield the same. Okay, so even if you do this, it's not bad if it is clearer for you. What in the end is the answer? 48 miles. That's the result of the conversion. So 1 hour for this car is equivalent to driving 48 miles. Let's try one more. Example 5. Okay, another about, motion. This is actually one of the typical type of question for rates, right? Rates that mean speed. Miles per hour, kilometers per hour, etc. So this one is a little different. It involves calculating a difference. Every time you see something like how many more, it means a subtraction between two quantities. So a subtraction between which quantities? It is the time Leona will take her to travel some distance and the time Tom will take to travel some distance, right? So we need first to find those times for each person. And for those times, what we have is actually some rates. Okay, here, this same distance refer to which distance? Notice, it says Tom drives 30 miles at some rate or some speed. If Leona drives at an average of 40 miles per hour, we are given Leona's rate. How many more minutes will take her to travel the same distance? So this same distance refers to the 30 miles mentioned at the beginning, okay? So what is the time that it will take Tom to travel that distance? Take a look. You multiply the 30 miles of Tom that Tom will drive by its rate. He does 1 hour or he does 50 miles in 1 hour. But I place it like this, like upside down, instead of putting 50 miles over 1 hour. I place it like this because I want miles to cancel with miles. Don't forget that. The placement of the order of the numerator and denominator is key in this type of question. So once you figure this out, then you need to convert, because this will yield hours for you, this first multiplication. Now, you want this in minutes. So multiply by a factor that turns the number of hours into minutes. 60 minutes divided by 1 hour. Why? Because I want hours to cancel with hours. So minutes are left. And doing this, we get 36 minutes is the time Tom will take to drive the 30 miles. Now, what about Leona? If you do the same for Leona, multiplying the same distance she's expected to travel by the rate she has, okay, the speed, then by the conversion factor between minutes and hours, we get 45 minutes for her. Yeah, simply said, she's faster, right? She goes or drives faster than Tom. So what's the difference between these two times? Simply 9 minutes. Okay, that's it. Well, let's see another one. Let's move on to example 6. To prepare for class, Mr. Chu has to print a number of booklets with P pages per booklet. If every 5 pages cost C cents to print and he spent a total of D dollars, how many booklets did Mr. Chu print in terms of P, C, and D? Now, this one is interesting because it's all variables. Notice that you start, okay? You start from something. You have some budget. And from the budget, you want to get to the number of booklets. So let's say the number of booklets is, I don't know, N, okay? Let's call it N. You want to get from D dollars to M booklets. But in between, there is a number of conversions to achieve, right? Because booklets means a number of pages in total. Also, the numbers of pages imply a number of cents. And of course, cents have to be translated to dollars. So you can express this operation, converting this into this, as a multiplication of D by a successive number of conversion rates, as we've seen before. Okay, you can try. Okay, the important thing to do here is formulating the chain of factors adequately. First, to connect or convert the dollars to cents. How do I convert this to cents? Okay, I can multiply this by a factor is 100 cents over $1, right? Then I need to convert the cents to number of pages. And then we have this factor or conversion factor, which can be set up as a rate. 5 pages correspond to C cents. So we set it up like this, 5 pages over C cents. Why placed in this order? Because we want to cancel cents with cents, then dollars with dollars, and so on. Now, what is the last part? Now we need to convert pages to booklets. Now, how many pages per booklet? P pages per booklet. So we say one booklet actually is P pages. So now in this multiplication, pages will cancel with pages. So finally, the result of this multiplication will yield the N booklets. So what is the value of N? Is what results of multiplying this, and dividing by 1, C, and P. So what is the answer? 500D over C times P booklets. This is the number of booklets Mr. Chu printed. All right? So corresponding to option C. Yes, Fabiana.
Sorry, teacher, can you explain again, please? I didn't understand very well.
Okay, sure. I think that in these questions, it's all the same approach. You need to set up a chain of factors in a long product where you multiply some initial quantity given in some type of units, for example here, a budget of D dollars, to find the equivalence in numbers of booklets. So that's why I said the problem to be resolved is converting the dollars into N booklets. What is N? in terms of D and the other quantities given. In order to find how many booklets can be bought with the dollars, first we need to know how many cents exist in the dollars. That's why I use the first conversion factor. With the number of cents resolved, it would be the result of this first product. Converting the number of cents to the number of pages that can be printed using that number of cents is using this conversion factor. 5 pages for C cents. So I set it up here, a multiplication for this corresponding factor. The multiplication of these 3 yields the number of total pages that can be printed. But since the pages must correspond to a certain number of booklets, depending on the number of pages that each booklet contains, I use this last equivalence to set up the multiplication by the last conversion factor, which is also another rate. 1 booklet corresponds to P pages. So with this, having the number of pages that I could have printed with the dollars, I know how many booklets I could have printed with the original D dollars. So the result of this successive multiplication will yield the total number of booklets. But as you can see, this expression is in terms of some variables or letters. It's in terms of D. We don't know what D is as a number. It's also in terms of C, the C cents mentioned here, and it's also in terms of P, the P pages mentioned there. So the expression, the numerical value of this product, you know that all the units will cancel except for booklets. And for all the quantities, multiplying D times 100 times 5 divided by 1 times C times P yields exactly 500D over CP. So this is the value of our N booklets here. Okay, this is what I'm expressing in this formula. All right. Well, so it's the same approach as in the previous questions, only that instead of using pure numbers, this time we are using some constant values expressed just as letters, right? But it's the same concept. Now let's see another question, or sorry, another topic. Now, talking about algebraic expressions, we'll practice in the following minutes how to resolve questions where you are asked to first combine like terms. You know, what are like terms? Like terms are algebraic expressions that possess exactly the same variables and with exactly the same exponents. For example, 7x squared is a like term with this expression, minus 5x squared. Why? Because they share the same variable and exactly the same exponent. But for example, 8xy versus 7xy squared are not like terms. Why not? They have the same 2 variables, x and y, but the second term has exponent 2 for y, while here the exponent is just 1 for variable y. So these are not like terms, okay? But these are like terms. You can say that one is like the other, algebraically speaking. So how do we combine like terms? Usually what we do, once we identify 2 terms that are like terms, you can just operate the coefficients. For example, if I see this and this, what is this? It's simply 7 minus 5 to x squared, and so on, right? There are other questions where you have to expand and factor expressions. Sometimes you have to combine fractions, but look, fractions of, you know, algebraic expressions, where the numerator and denominator aren't just numbers, but can also include variables. Then we also see some questions where we can flip fractions, that is referred to the division of fractions, and also split fractions. Let's see, beginning with this. For example, we have this long algebraic sequence, right? 2 times 2a squared minus 3a squared times b squared minus 4 times b squared minus a squared plus 5a squared b squared minus 10b squared. Which of the following is equivalent to the expression above? So here, the point is, first you need to open the parentheses, and then you need to reduce or combine the like terms. Okay? Like terms can be added or subtracted if you just operate their corresponding coefficients. Don't operate the coefficients of two terms that are not like, that are not similar. Okay? So what would be the answer? You can try. Okay, so how do we do this? First step is to get rid of the parentheses, right? So you can multiply 2 by all the terms in the first set of parentheses. Then to eliminate the second pair of parentheses, you can just change the sign of all the terms inside the parentheses because of the preceding negative sign, right? It would be something like this. When you multiply this, you get this. And when you open this parenthesis here, you just change the signs of all the terms inside. So it becomes negative a squared minus 5a squared b squared and plus 10b squared. Now you can identify pairs of like terms. For example, these two. 4a squared minus a squared, 3a squared. Then you have also these two. Negative 6a squared b squared and negative 5a squared b squared. Notice same variable, same exponents. So negative 6 plus negative 5, negative 11a squared b squared. And finally, these two are like terms. They both have b squared as the variable part, but the coefficients are negative 8 plus 10. So if you operate just the coefficients, okay, this is an operation of integer values. Negative 8 plus 10 equals positive 2. So 2b squared. Finally, that's the expression reducing all the like terms that were originally, okay, in the longer expression above. So this matches option C. Let's see another example. Okay, here, if it is not very clear, let me read it for you. It is 2 times x minus 4 times 2x plus 3, okay? And the answer choices 4x squared minus 10x minus 24. Option B says 4x squared plus 10x minus 24. Option C, 4x squared plus 10x plus 24. And option D, 8x squared minus 20x, here minus 24. Okay, that's it. Please try. Okay, so how do we do this? Actually, we have 3 factors here in this algebraic expression, right? In the algebraic expression, 2 times x minus 4 times 2x plus 3, we can decide to group the factors in order to do the multiplication. Some people prefer to multiply this one versus this one first. It's okay if you do that. Don't forget at the end to multiply that trinomial by 2. Or you can decide to incorporate this coefficient 2 in one of the factors in parentheses. For example, you can decide to multiply 2 and x minus 4. Then the resulting binomial multiplied by 2x plus 3. Okay, so let's pick this approach. You can multiply these two, x minus 4 versus 2. What do you get? Okay, use always your distributive property, right? How do you multiply this? This is the same as a times b plus A times C. So this is the principle when you multiply binomials in general or polynomials, right? In general. So how do we do this? 2 times x here, 2 times -4 here, 2x minus 8. Now this will be multiplied by the second term, that is 2x plus 3. Now this is a simple multiplication of binomials. How do we do this? Okay, follow the rule. Okay, first you multiply this and this. Number 1. Then multiply this and this. Number 2. Then multiply this term by this. Number 3. And finally, this one by this. Number 4. So you will have totally 4 products. Okay? If we do this, what do we get? We get this. The result of multiplying these two will be 4x squared, okay, is the product of these two. Then 2x times 3, 6x, negative 8 times 2x is this, and negative 8 times 3 is this. Then try to reduce any like terms in the sequence. Can you see any 2 like terms here? I think, oh, thank you, Fabiana. You already volunteered your answer to the question. But here, what like terms can we see? These 2. So if we reduce these 2 like terms, what we get is this. 4x squared, 10x. Very good. Okay, so this matches option A. All right, let's move to example 3. But before this, remember that in algebra, it's very important to master some key factoring formulas, right? That is to say, some identities or equivalences that always work, right? For example, the square of a binomial, that is the square of the sum of 2 terms, is this trinomial here, the square of the first term, plus twice the product of the 2 terms, plus the square of the second term. You also have the square of a difference. It's the same trinomial, but changing only the sign of the middle term. Then you have the famous difference of squares, this one, which can be factored as the product of the sum and difference of the 2 terms in the difference of squares. Okay? Now, there are some other combinations that may come handy from time to time. Who is legendary? Well, it was a French mathematician who proposed a combination of these 2. For example, if you add a plus b squared plus a minus b squared, let me here amend this. Okay, what do we get? If we just add these 2 trinomials, notice that you will just get canceled the middle term because they have opposite signs. So this yields 2 times the sum of the squares. But if you subtract the 2 identities of the square trinomials, something like this, the square of a plus b minus the square of a minus b, then if you change the sign of these terms and add with the trinomial above, what you get canceled are the squares, and the middle terms get added rather than subtracted. So you get 4 times a times b. Okay, sometimes if you remember this by heart, that you can save valuable time. Let's see now some more examples. Example 3. Which of the following is equivalent to 4x up to 4 minus 9y squared? Okay, they give you like these alternatives. Remember that sometimes you need to recognize, okay, a situation where you can apply one of the identities mentioned a moment ago. It may be there like hidden, right? in the expression. Okay, so what can we see in the expression given above? Can you identify that each of these two terms is actually the square of something else? If you were able to do that, then good for you, because clearly 4x squared is the square of 2x. Sorry, of 2x squared, right? The square of 2, 4. The square of x squared, x up to 4. So notice, what about 9y squared? Is this the square of something too? Yes. Take a look. This is the square of 3y. So we might say that the difference given in the question is actually a difference of squares. That is to say, is something like this. What would be our A and what would be our B in this difference? Well, clearly, it's like A is this part and B is this part, right? So that's the approach we are taking to this question. Take a look. If A is 2x squared, because A squared is 4x up to 4, and B equals 3y, and B squared is 9y squared, then you can factor this like this. This is A, this is B, so you have A plus B multiplied by A minus B actually, right? And this one here is A squared minus B squared. So we are factoring this difference as a product of a sum and a difference of two terms. Now, what follows? Well, it's just matching the correct choice, right? The one that corresponds is option D. Okay, let's move on. Let's try question number 4. Now here you have a trinomial, 16x up to 4 minus 8x squared times y squared plus y up to 4. Which of the following is equivalent to the expression shown above? Okay, you need to, what is the idea here? Try to factor somehow this trinomial. Can you match it perhaps, match it with any of these? Or perhaps this? Okay, try to use that hint. Notice here that it's a good idea always to try to attack the end terms. Those terms that are likely to be considered squares. So can you try to figure out what is 16 times x up to 4, square 4? Is this the square of some other term? Can you tell? 16x up to 4 would be the square of what? The square root of 16 is 4. And if you take a square root of this, would be x squared. So now you have that this first term is a square, something like an a square, right? What about the second or the last term in the trinomial? Clearly, this y up to 4 is the square of y squared. So what about this term here? Can we interpret this perhaps as this? As 2 times the product of A and B? Take a look. 4x squared times y squared, this would be 4x squared y squared. And if you multiply this by 2, then you get exactly this. And with a negative sign, okay, that means it is this pattern, right? Yeah, with this, we have already solved the question, mostly. Take a look. So if we use this idea, right, consider this as a match to this trinomial, then we can identify that this is the square of this expression, 4x squared minus y squared. The square of this binomial is the trinomial above. But now, we can proceed further. Why? Because this binomial here is at the same time a difference of two squares. 4x squared is supposed to be the square of 2x, while y squared is obviously the square of y. So if it is a difference of a square, can we further factor this difference? Yes, we can. We can say this, that this part here, this binomial, is actually the factorization of the difference of a square as 2x plus y times 2x minus y. Remember, if you multiply a plus b times a minus b, you get a squared minus b squared. So 2x times 2x, 4x squared. Y times y, y squared. So the difference of square, but in reverse. So now that we have factored this, remember that all the expression was set up to the exponent 2. So this exponent can be applied equally to each of the factors within. In the end, what we obtain is this expression. So this matches which one? Option C. Okay, so that's it. Well, that's an application of these factoring formulas or identities, like the square trinomial, the difference of squares. Let's see one more. Example 5. Notice now this is a little different. It's like fractions, but with variables or algebraic expressions in the denominator. How do we proceed here? 1 over x plus 2 over x minus 2. Okay, guys, what did you do when you had two fractions and you wanted to add them or subtract them, but the fractions had a different denominator? For example, something like this. A over b plus c over d. What did we do? We tried to find like a common denominator, right? We said, okay, the common denominator will be b times d. And then we find a factor by which to multiply this numerator so that we obtain an equivalent fraction. Since b times d, it's b multiplied by d, we need to multiply a by d as well. And in the case of the second fraction, since d needs to multiply by b to get this denominator, we need to multiply the numerator by the same factor too. So b times c or c times b. So in the end, we obtain the sum of these two fractions like this. The concept of giving a common denominator will not change because of using letters. It's the same. So try to do it like that. All right. So what do we get if we try this approach of giving a common denominator to each of the fractions and then the corresponding numerator for doing the sum? Because once we have the same denominator, we can add the numerators, right? Take a look. Our common denominator here would be just the product of the two denominators, okay? X plus 2 times x minus 2. So this will be the new denominator for each fraction. So we need to multiply the numerator by the factor they don't have. What would happen to the first fraction? Notice the first fraction, which is 1 over x plus 2, gets multiplied. In the denominator, we need to multiply by x minus 2 in order to obtain the common denominator, this. So in the numerator, we need to multiply by the same factor, because multiplying 1 over x plus 2 by this number, x minus 2, divided by the same number is like multiplying this by 1, right? You are not changing the value, only changing the form of the expression in order to make it have a common denominator. Similarly, the second term, you multiply by factor x plus 2 in the denominator in order to have the same common denominator, this one. So we need to multiply by the same factor the numerator. So what do we get this? From this, we get this. Notice, here, these two will get multiplied, and this will be the two fractions with the same common denominator now. 1 times x minus 2 is this. 2 times x plus 2 would be this. So now, since they too have the same denominator, you can directly add the numerators. What do we get? This. X minus 2 plus 2 times x plus 2. You can open the parentheses in the numerator in order to simplify the like terms. So x minus 2 plus 2x plus 4, this is what you get here, right? From this, eliminate the parentheses, and you get this. After reducing this term with this term, and this with this, you get 3x plus 2. So now, this is the final expression. We cannot simplify this anymore. This matches which of the options? Option B. Okay, let's try our next example. But you see, in order to add fractions with algebraic expressions, we use the same strategy that we use to add fractions that are heterogeneous. That is to say, fractions that have a different denominator. First, we find or convert both fractions to a common denominator. And then we add the numerators. Example 6. If x is greater than 1, which of the following is equivalent to x over the sum of 1 over x minus 1 plus 1 over x plus 1? How do we do this one? Here, it is useful to take into account the concept of flipping, okay? Flipping the expressions or the denominators. For example, how do we interpret this? A divided by B over C. You know, this is the same as saying this. A divided by B over C. But you know that the division of fractions is the same as a multiplication by the inverse of the divisor. A divided by B over C is the same as A times C over B. We reverse this one. So this is finally A times C over B. Okay, you can use this strategy when you have an expression like this, right? A divided by a fraction. This is what we call flipping the denominator. Okay, and what if the expression were like this? A over B divided by C. It is not the same as this one here. Why? Because if this is a division, okay, of two fractions, it is A over B divided by C. And remember, dividing or a division between fractions means that we need to reverse the divisor. So this is similar to A over B times 1 over C. Multiply this, you get A. Multiply these two, you get B over C. So this is the equivalence of this one here. Totally different from this one, right? Two different expressions. Be careful not to confuse the two expressions. So how do we solve this one? Okay, we can isolate and focus on this only. First, try to simplify that using the same strategy we used a moment ago. That is giving a common denominator, okay? So if we try to give a common denominator to the denominator only, which is a sum of two fractions, what would happen? Take a look. Okay, these two fractions in the denominator can be added using the strategy of converting each of them, fractions, to a common denominator. And what is the common denominator? Simply the product of the two denominators. X minus 1 times x plus 1. But converting the first fraction to the common denominator implies that we multiply the denominator by this factor. So we have to multiply the numerator by the same factor as well. In the second fraction, converting to the common denominator implies multiplying it by this factor. So the numerator 1 has to be multiplied by the same factor as we are multiplying in the denominator. So now what do we have? Since the two fractions have the same denominator now, we can add directly these two numerators. X plus 1 plus x minus 1, okay, the ones get canceled and you have x plus x, 2x. So this would be the equivalent of the sum in the denominator. What do we have next? Now we can proceed to simplify the expression using this concept of flipping here, right? Flipping the denominator. Exactly the same idea. A over B over C is actually A times C over B. So if we use the same approach, this numerator divided by the result of this sum would be x divided by 2x over x minus 1 over x plus 1. But what did we say about this? When you divide A over B over C like this is similar to A times C over B, or what some people call the sandwich rule, right? It's like A over 1 over B over C. You multiply this outermost and you multiply this innermost. The outermost product is above, the innermost product is below. So it's the same. So what happens with this x minus 1, x plus 1? This is equivalent to our C here. This gets multiplied by the numerator x. So we are multiplying now x times x minus 1 times x plus 1 over 2 times x. But here, the x can be canceled with this x. So we get the reduced expression like this. This one matches option D, of course, right? So that's it. Let's see one more or a couple more examples. Okay, in example 7, they ask me which of the following is equivalent to 30 plus C over 6. Now here, what strategy can we use? The strategy could be dividing the sum of this expression as a sum of two fractions. Okay? If you think that you have the sum of two fractions that have the same numerator, a different numerator, but the same denominator 6, what would be the result of splitting this expression? Okay, I think one of you already got it. Okay? Yes, that's correct, Axel. Okay, I think it's not that easy to notice that you can consider this to be exactly the same of 30 over 6 plus C over 6. So from this, clearly you can get the correct result, right? This one simplified would be 5. So 5 plus C over 6. Option D. Well, that's it. That's all for today, and thanks for participating.